The visa.
Oh, well, you get the visa on the website.
No.
Oh, because you're
I
getting
need an
money.
actual.
Okay.
Thank you. There's something magical about this audience, so it's settled quickly. We've installed monitors upstairs. So that in future, those of you, if you're so moved to sit upstairs, there's a much better view of the action than there was previously. At this point, I'll hand over to Christian.
All right, thanks. So it's my pleasure to introduce our first Colloquium speaker of the year, Anna Frebel, who is an associate professor at MIT. She's a very accomplished stellar spectroscopist. She got her PhD at the Australian National University, working on metal poor stars and the ARC process. She had postdoc positions at, well, here as a Clay Fellow at the University of Texas. And now she's, as I said, a professor at MIT. And so one of the things she's most well known for is her work on very metal poor stars, so stars that have something like more than 10,000 times fewer atoms of heavy elements like iron and other peculiar elements that she'll talk about in the periodic table. And so today she'll be telling us about a rare and prolific R process event in the dwarf galaxy, Reticulum II.
Thank you so much, Christian. It's a great pleasure to be back here, to see so many familiar faces. And I got a chance to talk to several here, and my voice in all my excitement has already gone a little bit rusty. But yeah, so I apologize for that. I'm very excited to talk to you about Reticulum II, this little ultra-faint dwarf galaxy. It's a really nice story that came about 2 years ago, and it was published last year in Nature by my student Alex G. So I'm mostly reporting on his work, but it's been a fun little journey. I want to start really broad to get everyone on the same page. You probably know that the Big Bang occurred some 14 billion years ago, and a few 100 million years after that, the very first stars emerged. And those were the stars provided the first light, but they also, upon explosion, provided the first heavy elements, heavier than hydrogen and helium. And so they seeded new generations of stars here that then formed not just from hydrogen and helium, as the universe looked like prior to the emergence of the first stars. And as it turns out, when you add a little sprinkle of metals to the gas, you can actually form low mass stars. We believe these very first stars were rather massive, which means they died really quickly as supernovae. And so the little low mass stars that were able to subsequently form, then it's possible, or at least we know, that some of them survived to the present day. And so from today's perspective, we are observing the second and later, these very early generations of stars that have low masses. And we think that they're formed in this very early era here. And in order to put this into perspective, I want to show you a little simulation. This is a cosmological n-body dark matter simulation that my former postdoc, Brandon Griffin, ran. And it just shows us this time scale of, well, actually it sort of starts around here and then up to the present day. You see in red and in yellow the sites of the first stars. So either little mini halos or first atomic cooling halos, which you also call the first galaxies. And you will see ultimately they come together to form the Milky Way. And this kind of hierarchical assembly of the central object here will again become important in the second half of the talk. But it also serves as a nice introduction to the topic of that. Ultimately, we have to put our knowledge together on stars, on chemical evolution, and on galaxy formation to truly understand the big picture and make progress. So you see a Milky Way type object is forming here, and it's surrounded by all these little dwarf galaxies here. And if I take that as at face value, Reticulum II, this little system I'm going to talk to you about, would be one of those little guys there. So a quick word on chemical evolution. If you think that this was the primordial cloud just made from hydrogen and helium, the first stars would form. In their cores, we have nuclear fusion going on through stellar winds. Material that's already enhanced in elements like carbon, nitrogen, oxygen would be put back into the reservoir here. But and of course, if they are massive enough and ultimately explode as a supernova, whatever was cooked up inside gets put back as well. Similar thing for low-mass stars. Quick intermission. Got too exciting. So low-mass stars, of course, also give things back to the reservoir, but I'm not going to focus on that. What we take away from this cosmic cycle here, because you have an enriched gas cloud here after one go-around, and then the next generation of stars forms, and with every generation, every star or all these stars that form will have a slightly higher amount of the heavy elements in them. And the sun probably formed when this cycle in this local patch where the sun ultimately formed had gone round about 1,000 times for reference. So we search for the stars that form as part of the second time here. And only the very first stars here provided the elements that were then provided to the gas from which our little metal poor stars formed. So consequently, older stars have a smaller amount of metals, of heavy elements than younger ones, and we look for these stars with the least amounts of heavy elements. For reference, Christian already mentioned this, the sun contains 1.4% of heavy elements from something like 1,000 go-rounds. The oldest stars have 10 to the minus 4 to 10 to the minus 7% of the heavy elements, so they are part of the second and the third and the fourth go-around. And here's a little plot that shows that in spectroscopic terms. Here's a spectrum of the sun, and you can see lots of lines, and it's very blended and very messy and hard work for those people who work on these metal-rich stars. I like to keep things simple because, the universe is complicated enough already. I look like metal-poor stars, and you can see here the iron over hydrogen bracket notation. It's a logarithmic notation, and negative values mean that it's less and less and less. And so here, if I take this star here, so thousands of the solar iron abundance, you see only 4 lines left in this region here. And then what we think is a second generation star here with minus 5.4, it's only this little guy left there, right? So this is really easy to analyze. I just want to throw in for fun, we recently found a star that actually had no ion lines, and you would think like, wow, that's easy. No, that gets really hard again because you have to get an upper limit, and then you have to kind of wonder because, we want to actually make measurements. Not measuring anything really just means we measure nothing. So it's a good problem to have. And so yeah, the periodic table was, and this is an important point for the remainder of the talk, but also I think in general to understand that through this chemical evolution cycle here, pretty much all of the elements were produced from day one, just in tiny, tiny amounts. And then with every generation here, more and more of all the elements was made. It's not that just the light elements were made in the first few generations, and then the intermediate ones in later generations, and then the heavy ones very, very late in the universe. Right, so it was all there from day one. And as you all know, we call this metals. So we look for metal-poor stars. That's what we usually do. That was my research group last summer. And so this is Alex here, who led this work together with Ani, my other student. We have shrunk a fair bit by now, but we had fun working on Reticulum II together. So the story I want to tell you today contains actually 3 pieces. This was just kind of to set the stage a little bit. The pieces are nuclear astrophysics, stellar archaeology, and dwarf galaxy archaeology. And as I will highlight, you really need to put all 3 pieces together in order to understand what's going on. I have worked on all 3 topics individually, And that helped to kind of see the big picture. If you leave one of them out, you're not going to move forward. And so that's why the story is really neat, because it combines so many different aspects. And suddenly it just all appears like it should be. So let me tell you how this all came about. So I'm going to start with a little bit of nuclear astrophysics and tell you a little bit about the origin of the elements. And you probably know most of that already, so I'm going to do this briefly. You know that light elements up to iron and nickel and zinc are produced inside of stars and then in subsequent supernova explosions. And you kind of see how this goes there in space. You just bang nuclei together and boom, there are new ones. Ultimately, you end up with iron. So that's during stellar evolution, and then all of that good stuff gets output when the star explodes. And but what about the bottom half of the periodic table, right? That cannot be done like this. So instead, we have what's called neutron capture, and that's responsible for pretty much all the other elements. There are two ways, though, so it's a little bit more complicated. There's slow neutron capture and there's rapid neutron capture. I'm not going to talk much about the slow neutron capture, but that happens in AGB stars. I am focused on the rapid neutron capture, and so far we didn't really know what the site, the astrophysical site was, but Reticulum II has given us some good clues. What's happening in a neutron capture process is that you have some sort of seed nucleus and you bombard it with neutrons, which means you need a bombastic neutron flux to actually have the neutron stick. So in a very short time scale, you're going to build up a really neutron-rich nucleus that then beta decays once the neutron flux has stopped. That's the difference to the slow neutron capture, where you capture one neutron and then you wait a little bit and then it beta decays and then you add another neutron. So the slow process is kind of one step at a time, and the rapid neutron capture is like, the traffic jam kind of. So that was a little animation here to show you this in a little better way. This is a piece of the charts of the nuclei. This is number of protons and number of neutrons. And the black squares are the value of beta stability. So that means stable isotopes that we know and love. And I'm going to let this run, and you will see that it will shoot out up here. So it makes neutron-rich isotopes. Everything below this value is neutron-rich. And then it will decay when the neutron flux stops. So I'm going to show. Observational evidence could be obtained but only by interpreting the spectra of type 1a supernova, a problem which so far has remained unsolved. Well, this basically still is an unsolved problem. It's just, I think now, so many years later, we are finally starting to scratch the surface of a solution. And we all know that supernova spectra are actually only so helpful. It's metal-poor stars with these R-process signatures that do help us to move forward. And so here is this star discovered by Chris Needham in the late 1990s. And in blue, you see the pattern that I just showed to you. And in red, you have the data points, and there's basically a near perfect match. For your reference, you see in purple here the pattern of the S process. So we can very well distinguish where these nuclei came from that we observe by just comparing the patterns. And I should highlight here also, so all the elements that we observe, they were not made by the star itself, but they're formed they were put into the gas from which these guys formed. And so the question is, what event put them in there? So that was my part on the nuclear astrophysics. We have to segue now into stellar archaeology. And here's my favorite picture of the Milky Way. We sit somewhere here, and we have all the metal-poor stars in the halo and also the dwarf galaxies. And we have found many R-process stars in the halo. And by many, I mean 3 to 5% of the stars that we have been looking at in the community, and it translates to about 30. Actually, we have a big campaign going on to find more, so we have about 40 now. of these stars with that characteristic pattern. It is unclear, well, we don't know how strong or how little this R process enhancement can be, because we have a tendency to only fish out the stars that have the strongest enhancements, because they're easiest to detect and to measure. And so there are still a lot of uncertainties, and it's very worthwhile finding a larger sample of these halo R process stars to learn about the R process. One problem exists, though, with halo stars, namely, we don't know what the origin of these stars is. And you might think like, come on, they're in the halo, you know, that's their origin. No, it's actually not. Because as you've seen in the little simulation, if you take into account the hierarchical merging of the galaxy, the halo is a conglomerate of all the stars that came from little dwarf galaxies that were accreted and eaten up by the Milky Way and then spilled into the halo. So they all formed somewhere else. They're probably actually older than the Milky Way itself, right? And so, as it turns out, that has been a major hurdle in the work to identifying the astrophysical site of the R process. So in stellar archaeology, what we do, and I hinted at that already, is that we find these stars in the Milky Way today. And if you're interested in knowing more about that, you can ask me later. I like to use the Clay telescope. Small little plug. I continue to use that at MIT, and it's still my favorite activity to do. So from the chemical composition of the stars, we get from using the Mike spectrograph and doing high-resolution optical spectroscopy, we deduce basically what the composition of this early gas cloud was, right? So we are just using the stars as tools to study the chemical composition of this early gas. And there's, of course, a little problem, because there's a mere 12 billion years in between, and no observations can really help me out there. So we need simulations to help with that, like the one I showed you. But another point that I wanted to make here is that when we look for stars with an iron abundance less or similar to -3, which is 1,000th of the solar iron abundance, then these stars are most important and most precious to us, because this little amount of iron here is small enough that you only need one progenitor or one progenitor event to account for all this material. Okay, and going forward now in the talk, it's pretty clear that it was one progenitor star for everything that produced the elements up to iron. And I want to call this a nucleosynthesis event. So we are searching for one nucleosynthesis event that made the heavier elements, because as I will show you, this is most likely not the same site. We have to treat this separately. And so by looking for stars with -3 or less, we are in a very, very interesting regime, because we get these clean nucleosynthetic signatures that tell us about the one progenitor. So for example, a population 3 first star, or a nucleosynthesis event like the one I'm going to tell you about in regards to Reticulum II. So to summarize that part, the galactic metal-poor stars are a great tool for near-field cosmology, because they're the local equivalent of the high redshift universe, right? And so the chemical abundances, they allow us to time travel. I wanted to add here, just for your amusement, what the periodic table would look like in color if only the R process was responsible for the production of heavy elements. Here you see it. So the color code describes the different processes and sites where these elements are made, because I'm showing you this to highlight you that the S process also makes all of these elements, but the devil is in the detail. The two processes produce different isotopes and different isotopic ratios within one element. So about half the isotopes are made by the S process and half of the isotopes are made by the R process. And I'm telling you this in such gory detail because I want to show you this, because this is the composition in the solar nebula, where of course you had 8 billion years of chemical evolution, and you have mixed you have a mix of S process and R process contributions from the various sites over a long time scale. And this is in the end what pans out. Europium is mostly produced in the R process in the sun, so in everything that led to the pre-solar cloud. And elements like barium and strontium here, they are mostly produced in the S process. And I think it's really nice to get a little bit more insight into the bottom half of the periodic table here and how it can all plays together. Okay, so we have some very big questions to ask now. And the first one, and that's the obvious one, is what is the dominant astrophysical site of the R process? And there have been several contenders. One is ordinary core collapse supernova. You need a lot of neutrons to have the R process going. Well, there's a proto-neutron-star in a supernova, of course, so that should give you lots of neutrons. Then there are neutron-star mergers. Well, that's neutrons galore, obviously. And then there are other options like jet-driven supernovae. It's unclear whether these guys actually exist because the few papers that have been written on this had apparently, and I talked to the authors, had the knobs turned that far that even the authors weren't quite sure if that was all physical anymore. But it's good to try sometimes. Related questions are, what is the rate and the yield of such an R process event, and is the dominant site changing over cosmic time? So let's get on it. Let me tell you a little bit about the potential R process in core collapse supernovae. And I want to kind of jump right in. So above the proto-neutron star, you have this neutrino-driven flux with plenty of neutrons. And so the R process happens behind the shock wave that then drives out and ultimately leads to the supernova explosion. And so, it just rides behind the shock wave and ultimately gets expelled. And theoretical yields for such a scenario are 10 to the minus 6 solar masses of total R process elements. I will tell you here already that for us observers, the total R process material is actually not very helpful because we can't measure all the elements. We can only measure specific ones, about 15 or so, sometimes a few more. So we need to know what the yield for a particular element is. And so europium is a good choice because, again, the R process makes most of that when you look at the universe's overall history, at least. And so that would be 10 to the minus 7.5 solar masses. Now, there are some pros and cons. The pros are that, I already mentioned, stars with an iron abundance of -3, and actually, I haven't mentioned that yet, pretty much all these strongly enhanced R process halo stars have a metallicity of -3. So they are in this one progenitor range. Yeah, we know that they need to have only one or few progenitors. So wouldn't it be nice to have a supernova be the site of the R process because it provides fast enrichment, and it could just be one site fits all. So you would just get everything in the periodic table from that supernova, and then your metal poor stars forms from the gas enriched by that event. And I have promoted that myself in the past because it was easy, and we didn't know better. There is a big con, namely that there actually are theoretical difficulties with producing elements heavier than barium. And that's actually a big problem that, of course, some of us, including yours truly, try to ignore because I showed you the pattern, right? And the pattern actually starts to be really strong and significant above barium. Okay, so let's see what neutron-star mergers have to offer. You see here the pretty LIGO picture, and I hope to hear more about mergers involving neutron stars at some point. But they come together, they actually tidally disrupt, and there are several places where the R process can take place in different ways, actually. So it's very complex. Here you see, and I always find it really fascinating to think that neutron stars, the most compact of objects, could tidally deform and then, basically become sort of snakes that just go around each other and eventually form a super neutron star. But that's actually what's happening and sort of shown here. And when, at contact here, that's when you have the R process going on. But there's also a neutrino-driven wind that comes out here on the edges, and there may be a connection actually to gamma ray bursts. I'm not going to go much more into that, but so there are plenty of opportunities there to make the R process, and so accordingly the yield is much higher, 10 to the minus 3 to 10 to the minus 4 for the total material, and that translates into 10 to the minus 4.5 solar masses of europium. So that's 1,000 times more than the supernova event, and there's no doubt amongst theorists that the pattern above barium, the amount of elements above barium can be very well made in this kind of scenario. So that's good. But the con, of course, is that these events are really rare. And how do you make a metal per star with just one progenitor while you need time for a neutron star binary to actually coalesce? Right? That was the big wrinkle until recently. And so I'm going to come back to that because I think we have an acceptable solution to this problem. So the timescale issue is big. Okay, so we are getting close to the stellar archaeology part. This is just a pretty picture of all the little dwarf galaxies that we know around the Milky Way, and Reticulum II is down here in the south. Just a quick word on ultra-faint dwarf galaxies. You probably have heard of the classical dwarf galaxies that are shown here. This is a plot of average ion abundance as a function of total luminosity of the system. And you can see there is a nice relation here, and it actually extends to these little dwarf galaxies that have 10 to the 3, 10 to the 4, so 1,000 and 10,000 solar luminosities only. And you can see that if you're keen on -3 stars, these bars here are not error bars, they are abundance spreads. So these galaxies have only very few stars, are very low luminosity as a whole, the galaxies of low luminosity as a whole, and they have huge ion abundance spreads. And the magic range is pretty well covered by most of these systems there. So they're also dark matter dominated. That can be measured, and that's why we think they're actual galaxies. You can see that on average they're very metal poor, and through HST color magnitude diagram analyses, it has been shown that at least I think 4 or 5 of these systems are truly old, something like 13 billion years old. Consequently, it's not hard to assume or to kind of figure that only few bursts of star formation must have taken place there. So these dwarf galaxies are ideal targets for dwarf galaxy archaeology, where we now use an entire dwarf galaxy rather than just one star to reproduce and reconstruct the properties of the early universe. Right? With my R process stars and my metal poor stars, as I said, in stellar archaeology, we study chemical abundances today, and that tells us about the chemical composition of the early gas cloud. And now we're using the entire dwarf galaxy as it looks like today to learn about what the conditions were in the early universe. And that gives us a few additional pieces of information that, as it turns out, are quite vital. I want to show a few pictures of Reticulum II. This is all stars in the direction of it. You can't quite see so much, but here you may see a little bit more. So it's actually a fairly large galaxy on the sky because it's only about 20 kiloparsecs away or so. It's the closest one found so far, which also means a few stars were actually brighter than 19th magnitude. 19th magnitude is the limit for what we can do with high resolution spectroscopy. So that was very, very fortunate. And as I will show, we observed 9 stars in that dwarf, in that ultra-faint dwarf. That is the one with the most stars observed so far. Actually, that's not true. Butes had some more, but Butes is bigger and brighter, so it has more to offer. We observed the 7 brightest stars, the red ones here, the member stars, up to about this gap here. And then some other people like in Röderer, they observed, I think, a few more there, and we're trying to work our way here, but it's incredibly hard to get any photons. And this is, again, just for your entertainment. So we, Alex, I should really say, Alex analyzed these stars. I mean, we had already an inkling when he went to the telescope because we saw a big fat europium line in RETII spectra, which got us very, very excited. And I made this joke, oh, Alex, maybe you found an opposite galaxy, haha. And actually, it turned out to be just that. So that was a bit freaky. But yeah, it was good fun. And here you see all the light elements, so the fusion type elements. In gray, you see the halo metal poor stars. And in color, you have all the known ultra-faint dwarf galaxy stars that have been observed up to end of 2015. And you can see that the colors, especially here in the case of chromium or nickel, lay pretty much on top of each other and on top of the gray data points. There are some outliers here and there, but of course the data for the ultra-faint dwarf galaxy stars is pretty ratty compared to halo data that's orders of magnitude, when the stars are orders of magnitude brighter. So I'm not too concerned about occasional outliers. And so overall you see there's a pretty good agreement. And what we learned from that is basically nothing except for that, yes, of course, a core collapse supernova produce these light elements because that is where you make them, right? So there's no arguing about that. So we confirmed what we already knew should be happening anyway. Okay, so far so good. Then we looked at the neutron capture elements, and this is the plot before we added Reticulum II. Again, gray is the halo stars, and in color you have the ultra-faint dwarf galaxy stars. And you see that the bulk of the colored points lays really low, and actually many have upper limits, again, owing to the data quality, but also owing to really low neutron capture element abundances. In this case, or for any of these stars, we can't actually tell whether the origin of these elements would be the S process or the R process because we don't have enough elements to make the pattern. Only when we can identify the pattern, we can truly say where they come from. If they're at low metallicity, it's more likely that they come from the R process, but we can't tell for sure. But what we wanted to prove when we set out to observe Reticulum was that, yes, it's another dwarf galaxy with really low neutron capture elements because it's such a telltale feature. Well, I'll show you how this looks in a moment, but I just wanted to share the data with you. So for comparison, this is an R process halo star, and you have a whopping barium and whopping europium abundance. And then this is a typical dwarf galaxy star. You can see the data quality difference. These wiggles are lines. These wiggles are noise. Okay, very important. There's a hint of a barium line here, but it's very low. Now, we observed two stars in Reticulum II. I have to make this a little bit exciting here. And look what you see. Well, nothing, right? And it's like, yes, this is what we wanted to find, another dwarf galaxy with really low neutron capture elements, because it must mean something. So adding more data to the pile, that's a good thing. And then we found these guys. Barium lines everywhere. And look, even europium, which is usually extremely difficult to detect, and the quality of the spectra is hideous. But because the overabundance of these R-process elements is so strong, even in these RETII spectra, you can still detect it. So I literally fell out of bed at 2 a.m. when Alex showed me the first star because, we thought that, was the wrong star, or metal-rich star. Metal-rich stars show strong barium lines, but europium lines, but that's not what we wanted to find. So hence the R-process galaxy, because 7 of the 9 stars that we observed show the signature. I have to remind you, in the halo, the frequency of R-process stars is 3 to 5%. Here we have 7 of 9. So that's a very different ball game. And here's the proof. We had the enhancements were strong enough, the data quality was just enough to measure at least 2 elements in this case. But you can see it fits, and it certainly doesn't fit here, right? This is what we had to show, that it doesn't fit the yellow, the S process pattern, but it matches up with the purple, which is the R process pattern. So R process elements galore in Reticulum II. What does it mean? Well, they are right up here, right? And actually, I can tell you these outlier halo stars here are the R process halo stars, right? So they fall smack onto those, and they look nothing like the brothers and sisters down here. But the other two stars, without enhancement, they fall right into the crowd here. Europium is a little bit harder because the line is usually much, much weaker, and so we don't have that much measurements, but it sits right here above the halo trend as well. So there's no doubt something unusual has happened in this dwarf galaxy, and we have to ask a few questions now. How rare could this event have been? And can we use the fact that all the stars formed in the same dwarf galaxy, can we use this to our advantage now to learn something new? And that is a big yes. And that is what really facilitated progress. And that cannot be done with individual halo stars, because now we use this concept of dwarf galaxy archaeology where we're not counting stars, we're counting galaxies. So we have an event of 1 out of 10 galaxies. Well, one R process event must have happened in 1 out of 10 dwarf galaxies. We haven't seen any of this in any of the others. And we estimated that all of the 10 UFDs, ultra-faint dwarf galaxies, had about 2,000 supernovae at that early time. This is a very rough calculation, but we're after orders of magnitude here, which means we have 1 R process event per few thousand supernovae, which is sort of consistent, or I should say not inconsistent with what other people are saying about the rarity of a neutron-star merger event, for example. But we could just derive this number without even considering the site. We're just looking at, how many supernovas would there be, and we get something like that out. So then we have to ask the question, how prolific was this event? And again, the environment that this dwarf galaxy offers us is key, because we can now estimate the amount of hydrogen of the system. And, it's iron over hydrogen. We usually never talk about the hydrogen, but we actually have to if we want to back out a yield for this event. And so by having information on the environment, we can bracket this between 10 to the 5 and 10 to the 10 to the plus 7 solar masses, and 10 to the 5 is simply the minimum dilution or mass you need in a star-forming cloud. Is also about the mass that is swept up by a supernova and polluted by a supernova, or an event, I should say, that has the energy of a supernova. I talked to many people, and people say that the neutron-star mergers have about the same energy. So that's equivalent. And then the maximum mass is, of course, the mass of the galaxy itself. So that's easy. And we can then play this game sort of forward on one side and then backwards from the abundances, and we can mix our neutron-star merger yield here as an example of 10 to the minus 4.5 solar masses into 10 to the 6 solar masses of gas. I just took the middle value here. And you can make a prediction that the europium over hydrogen abundance is minus 1.2 for a next generation star. Now we know Reticulum II is an incredibly low luminosity dwarf galaxy. It only has 10 to the 3 or 10 to the 3 point something solar luminosities. Most of the stars are around minus 3, between minus 2 point something and minus 3 point something. We'll see it on the plot again. And so the stars we observe probably are these next generation stars. So let's put it to the test. We did the same with a supernova, of course, that other yield, but let's talk about this first. So this is what I calculated here, 1.2. And I take a 2-dex error bar basically here, which reflects the uncertainty in the gas mass, right? We had a factor of 100 for the range of the gas mass. Same here for barium. And then you remember that the supernova yield was 1,000 times lower, so 3 decks. You just shift it down, and you're right here. So what do we learn from this? We learn 2 things. I think the stronger statement is we have ruled out core collapse supernovae as producers of this main R process that gives us the pattern, because it just cannot produce enough. Okay. What we also learn is that, yes, our range here is consistent with that of a neutron-star merger, but you could argue with me and say, like, well, maybe it wasn't a neutron-star pair, maybe it was a neutron-star black hole pair. Theorists now think that that's possible as well to get us enough R process elements. It could also be a jet-driven supernova, because their predictions are like that. So we have more work to do up here, but I think ruling out a major contender for the site of the R process is the piece of progress here that is robust. And of course, very important, because many people have been working on that. And since the publication of this, I've attended several nuclear physics meetings, and they all agree now they only want to work on neutron-star mergers anymore. So that's nice. But actually, the story isn't quite as harsh, because some of these points here are not upper limit. They're actual measurements here and there and there and there. So there is a tiny little bit of barium, and actually we can show the same for strontium, in these systems. Where does that come from? Well, remember, a supernova do produce neutron capture elements. They just don't produce it in the same way, in the same amount as a neutron-star merger would do. And so we need supernova to continue to produce small amounts of elements like strontium and barium, and maybe even tiny, tiny bits of europium, and basically unload that into every galaxy, because we have these stars down here as well. And you see the halo stars, some have incredibly low values. So I think coincidentally we have we killed 2 birds with 1 stone. We have a good or much better understanding now for what produces the elements and hence these stars here, but we're also having a good explanation for all these stars here, and we need both supernovae and neutron-star mergers to explain it. We can no longer hope for just one site. Okay, so the pundits might, of course, ask a few more questions. Can't you just increase the number of supernovae to, just up your yield? 1,000 supernovas would give you exactly as much as a neutron-star merger would give you. And that's, again, where it's just so nice that we're dealing with a little ultra-faint dwarf galaxy, because you add 1,000 supernovae to this system, it's going to go boom. It would not have survived until today, right? So we can nicely rule this out. Otherwise, that would have plagued us for quite a while. And then I just want to take a few minutes to talk about this issue of the time scale, right? Isn't the neutron-star merger simply taking too long to help? Wouldn't it produce the elements after the star formed? And as it turns out, there are now various calculations that show that the minimum amount it takes to coalesce is of the order of 100 mega years, 100 million years. And as it turns out, I messed it up, it's this one. And the amount it actually takes or the amount of time it takes for a little dwarf galaxy to come together and actually form second-generation stars also takes about 100 million years, because guess what? There were supernovae early on in the system, and they produced the fusion elements, but they injected a lot of energy into the system. So it needs to come back together, it needs to cool down to eventually form stars. And that small detail had been lost in the cartoon picture until now. And I'm certainly guilty as charged, but we just didn't have the right kind of observational evidence to guide us and to better consider this. So this was the picture before, right? And this is what I have promoted even in this talk until now. We have the primordial gas, you have your first stars, they pollute the gas, and then you form second generation stars. I didn't consider any dynamical effects, but we really need to give a little bit of a delay here for the system to do a breather and kind of come together and form stars. And in the meantime, we have just enough time for this neutron-star merger to go off and add to the already polluted gas here, and then you form your little guys. So I think it's a nice example where things sort of just fall in place. Of course, it's still a cartoon picture. Much more work needs to be done, but it's an exciting way forward, I think. So to answer the big questions, or at least I think we're beginning to have some answers. Core collapse supernovae as the site? Well, probably not, but neutron-star mergers are or would be consistent with what the abundances tell us. Again, more work needs to be done, especially with regards to other potential sites like these jet-driven supernovae. What is the rate and the yield of the event? Probably something like 1 per few thousand, and the total yield would be something like 10 to the minus 5 solar masses of processed material. And I think, or let me say, I value that the dominant site might not be changing over cosmic times. Sort of a bit of an Occam's razor argument, but we have this evidence from the so-called kilonova in the local universe that are these afterglows of the decay of the neutron-rich isotopes that clearly point to neutron-star mergers being responsible for the R process in the local universe. And I think it's just really nice if we now, or that we now have evidence that it would also be neutron-star mergers in the early universe. If it was kind of flipping around between supernovae and neutron-star mergers across cosmic time, I think that would just complicate our life even more. And so, I mean, that remains to be seen with time, but for now, my answer would be probably not changing. In the last 2 minutes or so, I wanted to offer you a little puzzle because the story is not quite done yet. We did find these 2 stars in Reticulum II that are not neutron capture rich. And the next challenge lies in explaining this system as a whole. And that means we have to not just understand what produced these R-process elements, but we also need to understand what the origin, the nucleosynthetic origin of these 2 neutron capture pole stars is. And so I hope that sometime soon someone will model this system to figure out whether we are maybe observing a sequential burst in star formation. As it turns out, the 2 neutron capture pole stars are the most metal poor ones in the system. Could be luck, could not be luck. So that needs to be kind of tested. So it could just be that they're formed much earlier. And it could just be that it's inhomogeneous metal mixing. Turbulence and chemical mixing is incredibly difficult. So, but it's so important to tackle this, I think. And this would be a really nice system to use as a test bed for this, to give us, to help us understand the system and also constrain metal mixing in general. And then this is my favorite idea because I've worked on a number of dwarf galaxies by now. And wouldn't it be cute if Reticulum II itself already had been affected by hierarchical merging, right, by the hierarchical assembly? Why would there be a galaxy that was like this from the get-go? So perhaps Reticulum absorbed a system like Segway 1, which is another really tiny, faint system with really low neutron capture elements, and that we proclaimed to be a surviving first galaxy a while ago. And so there must be more of these guys out there. And so maybe Reticulum ate a Segway. And these 2 stars simply came from a different galaxy. So we have, another level of complication to add. But it could very nicely, and I think elegantly, explain why we have 2 neutron capture pole stars in, kind of basically lost in this R-process galaxy. So I hope that will also be modeled in more detail than what we have started. And so we think that it is possible, but it's sort of at the resolution limit of the simulations. And so I would really like to see some more work in that area by my theorist colleagues. In closing, I want to throw out an update. Of course, the question is Reticulum II a unique galaxy? Can there be more R-processed galaxies? And actually, the answer is yes. Earlier this year, there was a paper on one star in the ultra-faint dwarf Tucana 3, and it has a mild R-process enhancement. It has a typical ultra-faint dwarf galaxy metallicity, so that looks really good. Just to show you, here's a praseodymium line, a samarium line, and here's europium. So in between, there was another dwarf galaxy discovered. So by now, we have 2 out of 12 systems to show some R-process enrichment. And as surveys like DES will discover more dwarf galaxies, we will continue to follow them up and hopefully increase this ratio in some ways. We shall see. So that will help to kind of firm up all these calculations that I showed you to kind of get a feeling for the frequency, for example, of an event like that. So finally, to summarize, I think a little bit of the future is here. Working with ultra-faint dwarf galaxies has really given us an incredible glimpse of what these little systems can provide astrophysics as a whole. They are so rich and there are so many topics that you can study with them, not just in nuclear astrophysics, but recently it was very nice to also add nuclear physics and nuclear astrophysics to the topics that can be addressed with these ultra-faint dwarfs. And so I hope I gave you a little insight into how to get or what it means to observe clean nucleosynthesis events and why they are so important, because they give us the site and environment information that we cannot get from metal poor stars in the halo. I already mentioned that, so we are hoping, of course, for more systems to be discovered, because right now we ran out of dwarf galaxies. It's a tough problem to have, but for once it's not telescope time that's limiting us, but actual objects. In the meantime, we keep, as I think mentioned, we have started a new big program to find more halo R-processed stars, because we do get much better data from them, and they will supplement the work with the dwarf galaxies to further pin down details on the site, and maybe eventually help us to distinguish between neutron-star pairs or neutron-star black hole pairs or other versions. And of course, that all helps us to prepare for the GMT. Right now, our limit is 19th magnitude, which means we're only scratching the surface of all the dwarf galaxies. They do contain more than 1 or 2 or 3 stars. We just can't access them right now. And so the GMT and GCLEF will, of course, enable us to go much fainter, and that's going to be fireworks. So with that, I thank you for your attention.
Well, thanks for a nice talk. So I'll open up to questions.
So first of all, thank you. That's really cool. Let me ask a little bit more about mixing. It just seems really odd. You have one very point-like event. It's very disruptive locally. And then somehow magically, when you form these stars, they're actually more similar than different, most of them. I mean, how surprised should I be by that?
Well, so if I ask theorists like Jos Van Hawthorne, who run simulations of this kind of breathing, right? So you have a little system that starts off with just a few supernovae, the first ones in the system, that ultimately produce the fusion elements. You have this energy injection, and so the system puffs up. And according to him, when it reassembles, it's actually just like mixing the dough. It gets fairly well mixed, actually, as it collapses again. So I think we shouldn't be so surprised that they are fairly similar, but you probably well spotted that they're not identical. And this is good enough. We don't know why there is a scatter of more than half an X here. Oh, actually, this included, it's more than it's more than 1 X. So there remain many questions, and so this issue of turbulence and mixing together with the dynamical effects of the system, I think have not been studied well at all. And so there's a lot more to do and a lot more to learn. And this data set will serve as a really good constraint on any of this work because, again, it's a really small system and probably had very little happening to it. So we even have fairly clean signatures or consequences of any of these, reassembly events and mixing things. But yeah, more work is needed.
If a single nucleosynthesis event produces an abundance of 10 to the minus 3, where are the stars that are below 10 to the minus 3 coming from?
Thank you for asking that question. That has caused a number of people a big headache. Now, the stars with -4 are not that far off, so a factor of 10 you can get by either screwing around with your supernova yield or your gas mass, right? That's not so bad. Now, the stars that we know with iron over hydrogen of -5 and even less than -7, we have this one star that has only an upper limit of -7, you're orders of magnitude below the one progenitor event phase, which means you have a big problem. You can't chop your supernova into pieces. So what people have done is they basically try to take iron away in the supernova explosion by coming up with a so-called mixing and fallback scenario, where parts of the ejector fall back onto the nasty black hole and only a fraction of it gets ejected out. That is the only way you can take metals, elements away in the universe. There's no other way. And so that is the trick. But it, of course, involves the special mechanism for the most iron core stars.
Actually, the question is prompted by what you just said. In a black hole neutron-star, I would think there would be some fallback of the debris power process material on the black hole. Have those calculations been done?
Not that I can tell, or at least the guys didn't talk about it. So I was just at a...
You actually get even more ejected out. When you get an all or nothing thing, you get the neutron star just falls into the black hole and out the start maybe. I mean, I saw several talks just recently at the INT in Seattle, and most of the calculations were actually based on neutron star black hole scenario, but yeah, that actually never came up. But I like what Ido said, all or nothing, that works for me. But of course, you have to consider it. Then the rate is going to be even, the frequency is going to be even less, right? And that's going to cause problems again. But maybe again, we can use Reticulum II to constrain some of that.
Would the neutron-star merger produce enough energy to increase the timescale past 100 million years, or is it not? It's just the amount of energy produced in neutron stars insignificant?
Yeah. So most people think that the energy of a neutron-star merger would be about that of one supernova, and one supernova doesn't do all that much to the system, as far as I understand. So I think that's not a crucial thing.
Maybe the last question?
You mentioned that there might be multiple populations or generations of stars in these galaxies. Why can't you do what you do in globular clusters in our own galaxy? In other words, get a color magnitude diagram, look at it, put on a stellar evolution curve, and see if there are multiple populations.
Ah, that's a good point. HST data is being taken off Reticulum II right now.
Oh, right now. Oh.
I mean, the proposal was approved and it's all up in the air, literally. So we're waiting. People have done that for
Other ones?
several others, or Thomas Brown from Space Telescope. The issue is the following, though. A, it's not that many stars compared to a globular cluster.
Right.
And there is a huge metallicity spread, which means your turnoff and your subjoint branch will be puffed up, and you have a hard time deciding member or not member because you have so few members.
You don't have the spectroscopy, you don't know if it is a member.
Oh,
Yeah.
no, yeah, no,
Yeah.
that's way too faint, right? That's why we do this.
Yeah.
And so there are degeneracies, and you can only have an isochrone with one metallicity, but the metallicity spread is sometimes 3 orders of magnitude, right? 3 decks. So that makes it very hard. So we can't really decide, is it a metallicity effect or is it a generational effect? And that has an impact on the age determination, which unfortunately, limits actually the accuracy on the ages of these systems because they're not globular clusters.
Looks like we're out of time, so let's thank Anna again.